in a kinetic investigation of the temperature dependence of a second order process, the following data is obtained. T1 equals, let me just get the numbers up here, 20 3C, K1 equals 2.0 times 10 to the negative 2 liters per mole per second, and T2 equals, T2 equals 30.
Apparition?
But no, this jumped down into my whatever. K2 equals 4.0 times 10 to the minus 2 liters per mole per second. Okay, this one starts to scare you until I remind you that all I'm asking you to do is write the expression for the equation needed to solve for the activation energy. Then ask you to solve it. Don't have time, because as it has already been mentioned, there's a lot of questions here. So you do need to know how to write the expression. And so T1 is equal to what?
293 Kelvin.
293 K. And T2 is equal to 303 K. And so we can now, on the scratch paper, because there is going to be a little derivation, but it's not too much, okay? You can memorize this equation, but rather than memorize the equation, you can derive it. The primitive equation you need to know is the Arrhenius expression, where recall, so this is scratch paper, what I'm about to do. Oh, I'll do it on another board. Scratch paper. K is equal to A times e to the minus e sub a over RT, right?
Yes.
Okay, so therefore the natural log of K equals the natural log of A minus e sub a over RT. Everybody with me so far?
Yes.
Okay, so the natural log of K2 minus the natural log of K1, so if I get it at two temperatures, this is a 2-point solution, is equal to the natural log of A minus e sub a over RT2 minus, and then I can say the natural log of A minus e sub a over RT1. And then I can take care of the rest by distributing this minus sign through. The A's drop out, and I distribute the minus sign, and that's equal to E sub A over R times, this is going to be now 1 over T1 minus 1 over T2. And now I can simplify this part by the rules of logs. What is the natural log of K2 minus the natural log of K1? How can I simplify that?
K1 over
Yeah, so natural log of K2 over K1 is equal to E sub A over R times 1 over T1 minus 1 over T2. And please note the features. K2's on top, and K1's on the bottom. K2's on top. It's the second term, is the one that's subtracted, and the one term here is the one. K1's on the bottom, and it's also the first term in this on the right-hand side.
If you wrote it the other way, would it still be acceptable?
I mean, if I reverse these? Yes.
And
Because this will reverse as well.
Yeah, you got to do 2 minus 1, right?
Yeah, the reason I like you to derive this is just so that you'll get the right result either way.
Okay.
So this is scratch paper. Everybody comfortable with this scratch paper?
Mm-hmm.
Okay, having armed ourselves with that scratch paper, I'm going to have to remember my expression, and now I'm going to start.
I did it myself.
Natural log of K2 over K1 is equal to E sub A over R times 1 over T1 minus 1 over T2, and then I can now substitute in the actual expression. So the natural log. Now, please note, 10 minus 2 liters per mole per second in both of them, right? So I can go natural log of, oh shucks, what's that? K2 over 4 over 2. Because the units all do drop out, or is equal to, because you can't have units in there anyway, E sub A over R, and I'm leaving it as R. Don't care which R you use, it's just different energy units. So E sub A over R over 1 over, and what was T1? 293 Kelvin minus 1 over 303 Kelvin. So that's all you had to do.
You have it the opposite way on yours.
Did I do K1 over K2? It works either way.
Oh, I see what you're saying. Oh, okay, that's why.
Yeah.
Okay.
Yeah. As long as I have this sort of a correspondence. See, this number corresponds to this one, this number corresponds to that
That makes
temperature.
sense.
Okay? Or I should have done it here, but yeah.
Can you use your pointer and do that?
Yeah,
so you're not in front
let
of
me
it?
use Mr. Finger so I'm not blocking it. As long as this corresponds to that, and that corresponds to this. Okay? That's the key for the equation to be written properly, because the most often encountered mistake when you're setting this question up is you swap these and they don't correspond to those.
Is that our
And then you get
final
some-
answer?
What? Yeah, that's all I asked for. I didn't ask you to solve it. All you do is write the expression. So it looks a lot worse than it is. And the scratch paper is definitely the part of this that makes it easy. So in that scratch paper, if you'll recall, the derivation wasn't that much to it. We had to start with a primitive law you need to recall is the the Arrhenius law, the Arrhenius equation. And once given that Arrhenius equation, we just took natural logs of both sides and just went to town, and then took the difference of the two. And so everything is, it's a pretty straightforward 1, 2, 3 step process. But it's easier to remember, because this keeps coming up. You notice how this keeps coming up? So we start with this, and we stand on that, and you derive it, and then you're standing on your feet. It's really where you should be, rather than trying to play Harry Potter and remember the spell. Okay? Because, which is great, and when you go to Hogwarts, that's what they'll have you do.
Graduate school.
Graduate school. Harry's got to be in grad school by now. And I think he has a really neat Mr. Finger. He has a wand. Yes. Okay. Is that good?